Probability. Let's learn about it. So first we're going to talk about simulation. In probability, what we're dealing with is the idea that over a long period of time, we can calculate an expected result. This concept is known as the law of large numbers. If we observe more and more repetitions of any chance process, the proportion of times that a specific outcome occurs will approach a single value, and the probability of any chance process is a number between 0 and 1 that describes that proportion of times the outcome would occur in a very long series of repetitions. So we know this concept already. We understand when we flip a coin over a long period of time, the amount of times that coin will land on tails is about 1/2 of the time. It will approach 1/2 of the time the more often we flip the coin. When we roll a singular die, the amount of times that die will land on the number 4 will approach 1/6 if we roll the die enough times, because there are 6 sides to a die and one of them has a 4 on it. So this is a concept that we should be familiar with. The thing that we want to not be mistaken about is these sort of myths about short-term or averages in probability. And both of them sort of describe the same phenomenon. So probability in general is the idea that randomness can be predictable in the long run. So we can make a prediction, and given enough time, that prediction will essentially become more and more accurate. Our intuition tells us that random phenomena should be predictable in the short term. However, that's not necessarily true. Just because I'm flipping a coin 10 times does not mean 5 of the times it will land on heads and 5 of the times it will land on tails. It will probably be close to that, but that doesn't mean it will be the case. Now, if I flip the coin 100 times, it will be closer and closer to half of the time. So the more often I flip the coin, the closer I get to 1/2, but that doesn't necessarily mean that in the short term it will be half, just because probability says so. The other myth we want to dispel is the law of averages. So this is the notion that because I knew what just happened, it changes the probability of something in the future. So just because I flipped a coin and it landed on tails this time does not mean it is more likely to land on heads the next time. That's not how probability works. If I flip a coin and then it lands on heads, then the next time I flip the coin, it's still a 1/2 chance that it lands on heads or tails. The probability for that outcome doesn't change necessarily just because I knew what previously happened. This is known as the law of averages. So one of the things we're going to have to do a lot in this unit is we're going to have to perform simulations for probability, right? So when we perform a simulation, what we're doing is we're using RNG, or we're using a coin flip or a die roll or something to simulate some chance process that's happening in the real world, but we don't have the capacity to replicate it in our setting. So instead, we're using the tools at our disposal, like and so on. So when we're going to perform a simulation, this is the format that not only will you use for this unit, but you're going to use this format for a lot of units whenever we have a situation where we want to test something. You're going to state explicitly what it is that you want to do. You're going to describe the plan that you're going to carry out. You're going to actually do it. So if you say in your plan, I'm going to use a random number generator to generate numbers between 1 and 10, then actually do it and record what you got. And then as a conclusion, use your results from your simulation to articulate what it is that you were testing out in the beginning. And again, we all have calculators and we all have the internet at our disposal for now, so there's nothing that says we can't just use random to sort this out. So here's a good example, right? So in an attempt to increase sales, a cereal company decided to offer a NASCAR promotion because people still like NASCAR for some reason. Each box will contain a collectible card with one of 5 drivers: Jeff Gordon, Dale Earnhardt, Tony Stewart, Danica Patrick. The company says that each of the 5 cards is just as likely to appear as any other one. So one of the fans decides he's going to keep buying boxes until she until she has all 5. It takes her 23 tries. That seems like a lot. So should she be surprised? So first we got to figure out what it is that we're actually trying to find out. The problem that we're facing is, what is the probability that it will take 23 or more tries for her to get all 5 cards? This is a perfectly reasonable probability question. What's the probability that it should take that long? If the probability is low, then she should be surprised. If the probability is high, then maybe she shouldn't be that surprised. So how can we test this out? Well, like we said, we only have so many things at our disposal. We have random number generators, and we have the ability to make graphs or plots, so let's use that. So what we're going to do is we're going to use a random number generator to represent the 5 cards, and we're going to see how long it takes us to get all 5. We're going to do this a bunch of times, and then we're going to keep track of how many times it takes us more than 22 tries to get all 5 numbers. So we're going to give Jeff a 1, Dale a 2, Tony a 3, Danica a 4, and Jimmy a 5. So we'll use a random number generator giving us numbers 1 through 5 to simulate each box giving us one of those cards. And we're going to repeat this over and over again until we have all 5. And then we're going to keep a dot plot of our results. So for example, if it, when it took us 9 tries, we'll put a dot there at 9. If it takes us 16 tries, we'll put a dot at 16. If it takes us 10, we'll put a dot at 10, and so on and so forth, right? And obviously, the thing we're curious about is how many times does it take us 23 or more tries to do this? So we're going to pretend that we've already done this a whole bunch of times. And if we look at our dot plot, we see that there's 23, or 22 and a half, so 23 would be right there. At no point during our simulation did it take us 23 or more tries. In 50 attempts, we never got more than 22 boxes, or had to buy more than 22 boxes to get all 5 cards. So there is at least less than a 1 in 50 chance that it would take 23 tries to get all 5 cards if they were actually randomly distributed, if each card was equally likely. So yes, this NASCAR fan should be surprised. Now this brings us to the idea of setting up what is known as a probability model. So a probability model is a description of some chance process that consists of 2 parts. There's a sample space, and there's a probability for each outcome. Sample space is represented with an S, and the probabilities for each outcome are represented by numbers and letters and all this other stuff, right? When we talk about a sample space, we are talking about the chance process of all possible outcomes, right? So the sample space is every outcome that we can get from our thing that we're doing. So here's the sample space for rolling 2 die. You can get a 1 and a 1, a 2 and a 1, a 3 and a 1, 4 and a 6, 5 and a 6, 6 and a 6. Since the dice are supposedly fair, then each outcome is equally likely. Therefore, each one of these die, or each one of these outcomes, has a probability of 1 over 36, since there are 36 total possible outcomes here. So the sample space is all 36 outcomes. Probability of each outcome is 1 over 36. Now, when we talk about a probability model, we're not talking about the outcomes, we're talking about the events. An event is a collection of outcomes from some chance process, or it can be considered like a subset, right? So it's like certain parts of the sample space that it is interesting for us to pull together. So what we do is we'll say, and we'll use the lettering of capital letters to describe events. So if A is an event, then the probability of A is written as P parentheses capital A. For an example, if A equals rolling a 5 with 2 dice, then we go back here and we find all of the outcomes that fit that event, right? Well, rolling a 5 can happen a few ways. It can happen by rolling a 4 and a 1, a 3 and a 2, a 2 and a 3, or a 1 and a 4. And yes, since the 2 dice are different objects, 1 and a 4 is not the same as rolling a 4 and a 1, right? So there are 4 out of 36 ways we can roll a 5. So the probability of the probability of the event A, in which A is rolling a 5, is 4 over 36. And there you go. That's it. That's probability models, basically. It does get more complicated. we have a set of rules for probability that we honestly just kind of need to memorize, right? So first of all, the probability of any event is a number between 0 and 1. If it's easier for you, think of it as 0% and 100%. You can't have less than a 0% chance of something happening, and you can't have more than a 100% chance of something happening. That just doesn't make sense. Now, all possible outcomes added together must have probabilities that add up to 1, right? Just like all possible, if you're thinking of percents, they must add up to 100%. If they add up to a number more than 1, then you messed up. If all outcomes in the sample space are equally likely, then the probability of event A can be found as the probability of A equals the number of outcomes divided by the total number of outcomes. This is what we just did, right? So if each of these are equally likely, for example, it's no more likely for us to roll a 2 here than it is for us to roll this 10. Since each of these outcomes are equally likely, then all we have to do to find the probability is just add up the outcomes that suit the event and divide it by the total outcomes. That's exactly what we did. Now, this is known as the complement. I like this rule. This is a very useful rule. The probability that any event A doesn't occur, or any outcome that's not within that event, it can be calculated by 1 minus the probability of that event. So the probability of rolling a 5 is 4 out of 36. The probability of rolling anything else is 32 out of 36. If two events have no outcomes in common, then the probability that one or the other is the sum of their, then the probability that one or the other occurs is just their two probabilities added together. That's easy. So if I want to find the probability of rolling a 3 or rolling an 11, I can add the outcomes for rolling a 3, so the probability of rolling a 3, 2 out of 36, and I can add that to the probability of rolling an 11, which is also 2 out of 36. So 2 out of 36 plus 2 out of 36, 4 out of 36. Now, this term, mutually exclusive or disjoint, is going to come up a lot. Two events are called mutually exclusive or disjoint if they have no outcomes in common and therefore can never occur together or at the same time, right? Simultaneously. And it's denoted as the probability of A and B equals 0. I can't roll a dice once and get both a 3 and an 11 at the same time. I can't roll a pair of dice at the same time and get a 3 and 11 at the same time. So the probability of that happening would be 0. So those two events would be mutually exclusive in this case. Here are those same rules, but given symbolically. So probability for event between 0 and 1. If S is the sample space of everything, then the probability of everything added together equals 1. Here's how you calculate a probability for an event. Here's how you denote the complement rule. And here's the addition rule for mutually exclusive events. Easy stuff. Now I know we're familiar with two-way tables, and they're going to come up again here. When finding probabilities involving two events, a two-way table is going to prove very useful for us. So, consider the following. Choosing a student at random, find the probability that A, that student has pierced ears. Okay, so we can look at the total number of students and then how many have pierced ears. So that would be 103 over 178. That's the probability, 103 divided by 178. What is the probability that they are a male with pierced ears? Well, males with pierced ears are pierced ears. Yes, I said it right. There's only 19 of those, so that would be 19 over 178. What is the probability that they are a male or they have pierced ears? Okay, this is a tricky situation. So how many males are there? There are 90. And then how many pierced ears are there? Well, there are 103. Now, based on what we learned just now, if these two events are mutually exclusive, then we should be able to add these together and get the probability. When we do that, we see the probability of getting a male or someone with pierced ears at random is 193 over 178. Now, obviously, the problem with that is that 193 over 178 is a number greater than 1. So that's impossible. That's an impossible probability. So why did this happen? Well, either we did the math wrong, which we didn't, or these two events are not mutually exclusive. The probability of A or B in this case doesn't equal just the probability of A plus the probability of B. And you can see that, right? There are 19 males who also have pierced ears. We counted them twice. We counted these males here in our 90, and we counted the males who have pierced ears again here in our 103. So what we should have done is added them together, but taken out the 19. So 193 minus 19 over 178. And we see that that would be 174 over 178. Which again makes sense, because if they are a male or they have pierced ears, then the only group that doesn't fit that category is the females without pierced ears, and there's only 4 of them. So 4 plus the 174 would give us 178. Now, what we just alluded to is called the general addition rule for 2 events. So the first addition rule we looked at is useful whenever they are mutually exclusive. If they're not, then we have to use a different rule. We'll use the general rule. This works anytime that we're adding 2 events. So sometimes we won't have mutually exclusive events. So what we'll do is we'll literally subtract out the ones that fit both categories so we don't double count them. So the probability of A would be this group, the probability of B would be in this group, and we would subtract out the ones that got counted twice so that we don't double count them. And we would be left with the 174 over 178. Now, we did this without really knowing this rule, so this is kind of intuitive. However, it should be useful for you to memorize this rule, right? Now, Venn diagrams are pretty useful when it comes to probability, right? So, and they're very good at explaining different probability rules. So the complement A, like the complement of A, or A, we'll see, contains all the outcomes that aren't in A. And you can denote that on a Venn diagram by highlighting the area outside of the circle, right? If A is represented by the circle, then everything that's not in A is everything outside the circle. If we want to show 2 events that are disjoint or mutually exclusive, that means they have no outcomes in common, so those circles within those Venn diagrams would not overlap. The intersection of the events A and B represents literally that part in the middle where they intersect. It's all of the events they have in common. In this example up here, it was the males with pierced ears. That is the intersection of males and pierced ears. Here, it's represented by this part in the middle of the Venn diagram. And last, we have the union of the events A and B. So that is all of the events that are in both A and B. That was represented by part C. All of the males all of the pierced ears or the males together. That would be considered the union of males or pierced ears. So this shorthand can be considered or, and this shorthand can be considered and. And here we see a Venn diagram representing exactly what it is that we were talking about. All of the males in A, all of the pierced ears in B, all of the males without pierced ears are in this area, and then all of the males with pierced ears are in here, and then all of the pierced ears who are not males are in this area over here. And everyone outside that group is right here. So event A, pierced ears, event A, male, event B, pierced ears, and this would be what that Venn diagram looks like. Conditional probability. So the probability that one event has happened, given that something else has already happened, is considered a conditional probability. You can think of it as, did A happen on the condition that B happened, right? The formula that we use is this right here. So this symbol here, this just straight up vertical line, that is the conditional probability symbol. You can read that, you can consider that as the given symbol. So this reads A given B. The probability of A given B can be calculated by finding the probability of the intersection of A and B, or the probability of A and B, divided by just the probability of B. Sometimes this probability is very easy to calculate, sometimes it's less easy to calculate. Let's look at some examples. So here we have a two-way table of the school, like in school and college, it's kind of like the subject, you know what I mean. So the different schools and then the grade levels within each school. So let's say event E is the grade comes from an engineering or physical science course, and event L is the probability that the grade is lower than a B. So if we ask what is the probability of E given L, that translates to what is the probability that the grade comes from an engineering and physical science course, given that it's lower than a B. So what we have to look at is first the intersection of A and B, or in this case E and L. And so that would be these 800 here. So 800 represents the probability of A and B, or the probability of E and L in this case. And then we look at just the probability of L. L is the probability that is lower than a B. That value is represented by the 3656 down here, the total amount of students who had a grade below a B. So this probability of E given L, probability that they were in an engineering physical science course, given that they made a grade below a B, is 800 over 3656. You can kind of think of it as the probability of this if we're only looking at this column, the total. Conversely, what is the probability that they made a grade lower than a B, given that they were an engineering and physical science student? So similar to how we started before, we look at the intersection of L and E, the intersection of the grade below a B and the engineering and physical science school, so that same 800. But now, the second event is that they were engineering and physical science students, so it would be 800 over 1600. So it's like looking at this probability, but only in this row. Now, based on that conditional probability rule, we can look at what is known as the general multiplication rule. So the probability that events A and B both occur can be found by taking this formula and rearranging it a little bit. We see that if we just want the probability of A and B, we can find that by multiplying the probability of A times the probability of B, where probability of B given A, where B given A is the conditional probability that event B occurs, assuming that event A has already occurred. Now, a lot of times, in the instances where this rule is used, the probability that A occurs is assumed. So what this ends up looking like is the probability of A times the probability of B. But it's important to remember that that's not always the case, and we could run into trouble if we forget that. The best way to prevent that from happening is by using something called tree diagrams. Tree diagrams are awesome for multiplication of events because they give you a sequential order in which things occur. So let's look at two examples for tree diagrams. The first one is pretty obvious, right? We want to find the probability of flipping a coin twice in a row and landing on heads twice in a row, right? So we start with tossing a coin. The way the tree diagram works is each event is represented by like a location on the branch, and then each branch has its own probability. So we toss a coin, we have a 1/2 chance of it landing on heads, we have a 1/2 chance of it landing on tails, and then from there we flip the second coin, and again we have 1/2 heads, 1/2 tails, 1/2 heads, 1/2 tails. So we see that there's 4 potential outcomes, one where it lands on heads twice, one where it lands on heads and then tails, one where it lands on tails and then heads, and one where it lands on tails and then tails again. So we can find the probability of it landing on heads by going along this branch where it lands on heads twice and multiplying the probabilities as we go. So the probability it lands on heads the first time is 1/2, and then the probability that it lands on heads again is 1/2. 1/2 times 1/2 is 1/4. We can also use this to calculate the rest of the probabilities fairly quickly. However, I don't want to do that right now. Let's look at something slightly more complicated, right? So the Pew Internet and American Life Project finds that 93% of teenagers ages 12 through 17 use the internet, and that 55% of online teens have posted a profile, of online teens have posted a profile on a social networking site. I imagine that number is a lot higher nowadays based on when this was taken. So the question is, what percent of teens are online and have posted a profile picture? I want to know both. So what this is kind of getting at is similar to the question, what is the probability that we randomly select a teenager and they are both online and have posted a profile on social media? What is the probability they have done both? So first we have the teenagers who are online. So yes, they are online, or no, they are not online. Interestingly, if they are not online, we know whether or not they've posted a social media profile. It's no, they haven't. There is a 1 out of 1 chance that they haven't, right? It wouldn't make sense. But more interestingly, if we randomly select a teenager, there's a 93% chance, or 0.93 probability, that they are online. And on top of that, from there, if they're online, there is a 0.55 chance that they have posted a social media profile. So if we want to find the probability of getting a randomly selected person, or teenager in this case, who is both online and has a social media profile, it is the probability is equal to 0.93 times 0.55. Likewise, the probability of finding one that is online but doesn't have a social media profile would be 0.93 times 0.45. If you added these two probabilities together, plus the probability of these two, obviously this one would be 0 and this one would be 0.07, they would add up to 1. In this case, though, the probability that we're interested in, 0.93 times 0.55, is 0.5115. That is the short version of the probability that we are covering in this first week and a half or so. Hopefully most of this stuff is review for you, but just in case it's not, every rule, every thing that is interesting for us should have been covered here. So I hope this was helpful.